Okay, so I already read it to you, but I'll read it again just for the recording's sake. So if you, I don't know, did nothing for the past couple minutes, here's your chance to hopefully figure it out. Previously, you saw a situation where the total number of times a dog has barked was a function of the time in seconds after its owner tied its leash to a post and left. Less than 3 minutes after he left, the owner returned, untied the leash, and walked away with the dog. Table 8, could each value be an input of the function? So actually, before you answer that, can you tell me, like, between the two things being compared, the number of times a dog has barked and the time in seconds, which would be the input? Where do we graph inputs? What axis do we put them on? Okay, good. So the x-axis is where we put whatever our input is. So then table 9 is our input, the number of times a dog has barked, or is it the time in seconds? Time in seconds. So when it's asking, could each of these be an input? It's asking, could each of these be a time in seconds in this situation? So table 1, could 15 be a time in seconds in this situation? Yes. Table 2, could 84.5 be a time in seconds for this situation? Why not? Is it just a guess or where are we? Okay, someone else at that table? Could I have 84.5 seconds in this situation? Okay, back to you. Table 3, what do you think? 84.5, is that a possible amount of seconds we can have in this? Yes. Can you have a fraction of a second? Does 84.5 fall within 3 minutes? So yeah, that can be a possible amount of seconds in this situation. Table 2, can 300 be a possible amount of seconds in this situation? Why not? Good. So 3 minutes. I mean, is it possible to have 300 seconds ever? Yes, but 3 minutes is when the time stopped. All right, because it only measured how many times the dog barked while the owner was gone. At 3 minutes, the owner returns. How many seconds are in 3 minutes? 108. So anything under 180, not including negatives, obviously, would be possible, even the decimals in between. But 300 is not, because that would exceed the time frame. Does that make sense? That's what you really should be asking yourself. So you could say, because 300 seconds exceeds 3 minutes, or 180 seconds. All right. Table 4, what about, could each value be an output of the function? So if our input is time in seconds, then our output would be the number of times the dog has barked. So table 4, is 15 a reasonable number of barks for the dog? Yes. Table 5, is 84.5 a possible number of barks? No, why not? Too many barks within the time. What do you guys think? There's 180 seconds. Do you think that within 180 seconds that a dog could have barked 84 and a half times? What is wrong with the 84 and a half? It's not that it's too high of a number, it's that the fraction of it. So yeah. No, because you can't have half a bark is the reason why you can't. Table 6, could 300 be a possible output, a possible number of barks? Do you think the dog could have barked 300 times within the time frame? Okay, is it why?
Way too many times for 3 minutes.
Okay. Um, that's like, I guess, a matter of opinion. I don't necessarily think it'd be that unreasonable. If a dog is barking, some of them bark multiple times in just 1 second. So I don't think 300 is necessarily so high that it's impossible. If we said maybe like 1,000, like that might be more unlikely. So you could probably make a good argument for or against. I do think it's possible. I think if we did 2 barks a second, let me do 2 times 180 real quick. I'm pretty sure that's over 100. I'm sorry, over 300. So if they just bark twice in a second, which is really actually feasible for a dog, then it would exceed 300. So I'm going to go with that. That could be a possible output. It would just be that the dog is barking almost the entire time. Once we start getting higher numbers, maybe like 1,000 or so, maybe even like 400 might be really unlikely, then it's definitely probably not going to happen. Okay, so that is what we are covering today. We are talking about all the possible inputs and outputs of a function. And we call inputs and outputs lots of different things. Inputs are our x's. We also attach the word domain to them. We're going to attach that word again today. We're going to ask what's the reasonable domain, and you're going to tell me what's the reasonable inputs. We also call it the independent variable. So sometimes it's not clear what should be the x. You have to figure out what is more independent than the other thing that's being. Guys, stop staring at your computer screens with your polar surgery. Outputs, we also call a lot of different things. What do we call outputs? The y's, the range, and the dependent variables. I've given you guys lots of little tricks to remember which and which. I'm gonna continue applying those. But now instead of just saying what's a possible input, we're gonna say what's a reasonable domain. What's a reasonable range for this situation. And that's for you as practice in the real world. I see some people writing, so I won't switch it yet. But I record every day, so make sure you're staying caught up with the class. We only have one more lesson, and that's tomorrow. Your binder check is this Friday. And also tomorrow is when I'll give you the practice constructive response test officially. You're welcome to grab it from the bin anytime you can. The final exam review is also in the bin too. So up to you if you want it early. I only give it to you like a day before it's due because, let's be honest, some of you will not work on it until then. So I will check that practice test during binder check. And you have technically two practices today for lesson 10 and 11, so make sure you do both. I tried to only pick the really important problems on there. All right, so those two. Study materials are all available, so make sure that you are ready for our last unit test. We're doing that Tuesday next week and retaking it Thursday next week. And then that's it. There's no like additional opportunities after that. It's just final exam review. Questions? Okay, so we kind of touched on this already, but there's lots of different names for inputs, outputs. Now attach domain and range to it. What's an easy way to remember which is the domain and which is the range? Okay, domain is the X. An easy way to remember it is Dr. XY. Okay, where domain is all the X's, range is all the Y's. So for this first activity, I'm going to give each group a set of cards, and they're going to have numbers on them. You're going to, based on whatever situation is on the screen, it's also on your paper too, you're going to decide what are all the possible inputs for that function. So kind of like we did in the warm-up. They're not necessarily saying my input is this. You have to like read the context clues to figure out what it is, and then what are possible values based on the cards. You're going to sort them. Each stack will have enough that if you guys wanted to split into like twos and twos, you could do that. Otherwise, you can just put the duplicates aside and do it all together. It doesn't really matter. When we do go over it, you will write our final answers. But here's the first situation. The area of a square in square centimeters is a function of its side length s in centimeters. The equation a of s equals s squared defines this function. You and your groups will figure out what's the input and then figure out what numbers the input could possibly be and not possibly be. In order to figure out which numbers could be possible inputs, you have to figure out, based on the situation, what the input is. So table 7, between the area of a square and the side length, which would be considered the input?
The area.
Actually, the side length. Because, first of all, the area of the square would depend on the side length. The side length is what's independent. The area depends on the side length. And also they gave you the equation written in function notation. We know that when something's in function notation, the input or the x is always in the parentheses. And in this case, it was s for side length. Does that make sense? Because that's like 2 questions on your test. Got to be able to figure out what's my input first. It's my side length. That's what would be plotted here on the x-axis. Now you need to look at all your numbers and decide what are possible side lengths. Table 8, can you tell me some possible side lengths?
Good point.
For what? Okay. Any others that you think are possible from your piles?
15.
Okay. Is that all?
Nine.
Okay. Any others? So let me, while you're thinking about it, let me just point out there's different types of numbers, right? Like there's positive numbers, there's negative numbers, there's decimals, there's whole numbers, there's fractions. Can side lengths be decimals? Like when you measure a length, it's gonna be decimal. So any decimals that are also not negative, because when you have a negative side length, any positive decimals should be in your list of possible inputs. So class, what are some more possible inputs?
72.
All right, any others? Cool. 4. What about fraction? 25/4, is that possible? When I divide it, would it be positive? It would be decimal too. I mean, decimals are fractions and vice versa, right? So any positive fraction that's on your list, it can also be 3/5. Table 9, what are some impossible inputs or side lengths? All right, any others? Oh, negative what? All right, any others? I guess you're right, yeah. We can't have 0. We can't measure something for length and get 0, I guess. Any others out there? Class? Sorry, what? Because I don't have the list in front of me, so I'm going based entirely off of what you said. To summarize, anything that's possible for side length or possible/reasonable is the other words that they use. Would be all positive real numbers. That's more of the verbiage that they'll use on your test when we talk about possible or reasonable. When I say that, one, I'm saying that it can't be negative. And real numbers means that it can be like whole numbers and all the decimals in between them, like fractions and decimals. Does that make sense? 0 is neither positive or negative, so that's why it's not. The impossible inputs would be any negative numbers. Integers would technically just be like whole numbers, not decimals. So we'll say negative real numbers so that if there are any negative decimals, you know those aren't. Okay, questions, comments, does that make sense? Do we kind of see how it's supposed to be now for the rest? Okay, so now here's your next situation. I'll only scroll halfway because I know some people are writing. So situation 2 that you're gonna sort for now. A tennis camp charges $40 per student for a full day camp. The camp runs only if at least 5 students sign up, and it limits the enrollment to 16 campers a day. The amount of revenue in dollars that the tennis camp collects is a function of the number of students that enroll. So now you're sorting based on that input, and I'm not telling you what the input is. You have to figure out what's compared. What is the input? In order to figure out what's possible or impossible, you have to know what you're talking about, right? So you have to know what the input is for the domain builder synonyms. Table 1, in this situation, what is my input? What would I graph on the x-axis? Okay, number of students that sign up. It's not necessarily just going to be 5, but number of students that sign up. That is independent. What is dependent is the revenue in dollars Because that would obviously depend on how many people sign up, right? Does that make sense? So figure out what's dependent, what's independent. That's to me, I think is the most helpful, but maybe not for you. They did give you a equation this time, and you know that what's in the parentheses would be your input. And they defined n as, or I guess they didn't define it at all. But if they did, it would be the number of students that sign up. Now, table 2, what are some possible inputs or values for the number of students that sign up? Any other? Okay. Do you guys agree with that? So while you could have 4 students like in the real world, for this situation, they did give you some specifications. Kind of like in the warm-up, remember like the dog was only there for 3 minutes, and so that's why 300 seconds was impossible, right? Because of this stipulation, that is the only reason why 4 is not possible. Like, yes, you could have 4 students, but in this situation, you need at least 5 for this work. Does that make sense? Any other issues? So another stipulation, it says up to 16 campers. So that means really for this situation, out of your list, only 9 and 15 work. But what do all these numbers have in common for the reasonable opinion? How did you know that it wasn't any negatives or decimals or anything like that? You can't have negative amount of students and you can't have a fraction of a student in this situation. So on your test, what it'll probably say is positive whole numbers. These are whole numbers, those are not decimals. Or positive integers would also technically be that too, not decimals. The positive whole numbers from 5 to 16. Maybe I'll put the actual word instead of that. Then it's not subtracting. Take your notes later. Basically, my input, my domain can be positive whole numbers from 5 to 16. Everything else, including the decimals, including the fractions, and of course, anything that is negative, are not reasonable for this situation. Does that make sense? All right. So then one more situation with the card sort, and that is going to be, and I know people are writing, so I won't flip the screen yet, but that's going to be the one about degrees in Celsius and degrees in Kelvin. You have an equation in that one. Figure out what's your input and output, and then figure out from your cards what would be a reasonable input or output. So table 3, you're on deck, but let me read it. You guys were looking at the relationship between temperature in Celsius and the temperature in Kelvin, represented by function K. That's this equation written in function notation, where C is the temperature in degrees Celsius and K of C is the temperature in Kelvin. So table 3, what would be my input? If I was graphing this, what would go on the x-axis? Okay, good. Now, when we're talking, normally we talk about like what's independent, what's dependent. Based on how this is set up, the degrees in Kelvin depends on what the degree was in Celsius. I mean, I know they're technically like both measuring temperature, like they kind of depend on each other. But the way that it's written in function notation, you know that what's in the parentheses is your input or your x, right? So you were deciding what are some possible degrees Celsius, basically. So class, let me ask you, is it possible to have negative degrees Celsius? Is it possible to have decimals of a degree Celsius? Could you have a decimal of Fahrenheit? Is that what's throwing people off?
Okay.
You could, like, if you ever take your temperature with a thermometer, right? When it's against, I think, hold on. Never. What else? So it can be decimals, it can be negatives, can it be positives? Can it be fractions?
Yeah.
So if it can be decimals, it can also be fractions, yes. So is there anything that's excluded? Is there anything that was impossible? Do you guys remember what we call it when it can be anything? Anticipating the answer before I finish asking it, yes, it is all real numbers or the domain. But we talked about that once before, if you guys remember. If there's nothing that can be excluded, then it's all real numbers for our domain in this situation. There was nothing that could be excluded, so you put none for that. I don't have a special word for that. But all real numbers basically says it can be positive, negative, decimals, and fractions are the same as decimal. Questions? Okay, that's it for that activity. So make sure you have good notes, and then I'm going to direct you just to the screen, this next part, and you're just going to look at it, okay? You can put your card sort back together and put it in the baskets that are at your table. Okay, I know that was fun and you guys really enjoyed it, but we gotta move on. So. All right, I need your eyes on the screen because it's not on your paper, it's only on the screen. You could write it down if you want to, but you just need to notice something, okay? In each situation, we only talked about the inputs. If we talked about the outputs, then, you know, we're deciding what's a possible dollar amount that we could have raised, what's a possible temperature in Kelvin, and what's a possible area, right? Like those might be different than how we measured the inputs. Hopefully you guys know like what's reasonable in each situation. But one thing that you will have to do, especially like on your constructed response test for one of them, is decide whether or not you should connect the dots once you graph it, or just leave them as individual dots. So, for example, in this first situation where we had the area of a square and the side length, we connected the dots because you could have all of these numbers for the side lengths and every decimal in between, right? We talked about that earlier. Now for the outputs, can your area be a decimal? Yeah, like if my side length was a decimal, it's a good chance my area is probably going to be a decimal. So because of that reason, we did connect the dots because it can be everything in between those whole numbers on each side. For the other situation, situation 2, where we had the campers and the revenue. If you're asking yourself whether or not you should connect the dots or not, you need to ask yourself the same questions. Can I have a decimal of a student? So that right there kind of tells me I probably shouldn't connect them. But even if you could, like let's pretend you could, are they charging every single value in between these numbers? I know you can have a decimal of $1, but in this situation, they were charging $40 per campers, and the campers went from 5 up to 16. I'm gonna skip a bunch of numbers, but if this was my input-output table and I'm charging $40 per camper, then for 5 campers, it would be $200. For 10 campers, it would be $400. For 16 campers, I'm not going to do that math right now, but what I definitely shouldn't have as an output would be like $401, right? Like there's no way they're charging someone other than $40. So it has to be like multiples of 40 from when the inputs are 5 to 16. So there are situations like that where instead of connecting the dots, I would just leave them as separate, distinct dots. Does that make sense? Any questions on that? You're really just seeing like, is that possible to have a decimal of a person? Would it make sense? Should I connect them or should I just leave them like that? All right, but now let's do maybe just a couple activities on lesson 11. I know it's a lot, but let's do it so that way tomorrow's could be our last lesson and not be a combo lesson. So you have different graphs that look like what you see on the screen on the back of your notes for lesson 11. You are going to basically match which function goes with which graph. Here's the descriptions. I don't think you have the descriptions, or you do have the descriptions. So you're going to first match which function goes with which graph. A child gets on a swing in a playground, swings for 30 seconds, then gets off the swing. Here are descriptions of 4 functions in the situation and 4 graphs representing them. The independent variable in each function is time measured in seconds. Just so you know, our independent variable for all of them will be time measured in seconds. Our x-axis for all of them will be seconds. You're going to match each function with the graph that could represent it, and then label the axes with the appropriate variable. We already labeled the x-axis for seconds. So function 8, we have the height of the swing in feet as a function of time since the child gets on the swing. We have function R, the amount of time left on the swing as a function of time since the child gets on the swing. Function D, the distance in feet of the swing from the top beam as a function of time since the child gets on the swing. And the total number of times an adult pushes the swing as a function of the time the child gets on it. That's a big mouthful to say as you go back and reread it as you need to. You're matching which graph goes with which situation. Give you less than a minute to do that. What match were you able to make? Okay, so distance in feet of the swing from the top beam as a function of time since the child gets on the swing. So when we're talking about from the top beam, here's a picture of the swing down here. Right? Does the distance from the seat of the swing to the top ever really change? So should it go with the one that says it's decreasing over time? Which one should it actually probably go with? This one, where it's staying at the same height the entire time. To label the axes, that would be the distance in feet. I mean, really, you should probably include almost all the details, but it's distance in feet from the top beam, or in other words, it goes to function. Does that make sense? Table 5, tell me another match that you were able to make. Function beam shows which one? Okay, this one. This one, you guys don't know like what these are called yet, or maybe you do, maybe you saw them in middle school. But these are piecewise functions. Those you're gonna have more practice with tomorrow. But function H says the height of the swing in feet as a function of time since the child gets on the swing. You guys agree with that? The height of the swing in feet as a function of the time since the child gets on the swing. So when something's swinging, the height is changing, right? Is it going from like, say these are counting by ones, from 0 to 1, then 2, then 3, then 4, then 5? Is it changing like that? Or how does it change when you swing? Goes up and then down, and then up and then down, right? So which one should function H probably go with then? The bottom right, the one that goes up and down constantly. Because yeah, the height for a swing would increase and decrease. And it has parts where it's like kind of getting momentum and then slowing down. So function H would probably be better with this one. All right, so already wrote it down. And the axes, the y-axis would be the height of the swing in feet. And that's out. Okay. Table 6, tell me one more match that you made. You said S. This one? Okay, so function S says the total number of times that an adult pushes the swing as a function of time. You guys agree with that? Because when you count like the number of pushes, it's like 1, 2, 3, right? It's not happening necessarily every single second. So that's why there's parts where it's like the same number of pushes that you just did, right? So that one does match with function S. That y-axis would be the total number of pushes. And then process of elimination. Function R goes with this one, which is the amount of time left on the swing as a function of the time since the child gets on the swing. So they're both seconds, but this one would be time left on it. Whereas this one is like time on swing so far. All right, good. Any questions, comments, concerns? Let's see what we can squeeze in. We might have to finish it tomorrow, but let's do a little bit more since we just talked about it. We need to talk about the domain and range now of all these different types of graphs. Notice that the axes are not labeled with numbers, so that's why you do need some information. I have it up here in the top corner. I don't think it's on your paper, so just we'll reference this each time you need to go on there. We have the child is given 30 seconds on the swing. That means here's where it hits 30 seconds. While the child is on the swing, the adult pushes the swing a total of 5 times. That's a different function. The swing is 1.5 feet above the ground.
So that means here's where it's 1.5. The chains that hold the seat and suspend it from the top beam are 7 feet long. We don't need that for this function. That is height of the swing since the child gets on it. And the highest point that the child swings is up to 4 feet above the ground. So it goes up to 4. Domain refers to all the what in a function? All the x's. So look at my x-axis. It is going to be all the numbers, including decimals in between, right? From what to what? Where does my x-axis start? Okay, 0, because right, you can't have negative seconds on the swing. And when does it end? So here's one way it might be expressed. Real numbers from 0 to 30. That implies it can be the decimals in between. But when we say from 0 to 30, that kind of makes it positive numbers only, but they might even add the word positive. All positive real numbers from 0 to 30. Okay. What is the range referring to? All the y's in a function. So now look at your y-axis. Can my height be a decimal? Yeah, you can have a decimal of a foot. Can it be negative? So for this height, this range, you could say all real numbers from 1.5 to 4 in this case. It is not starting at 0 for this one. It's not going above the 4, so you want to say just all real numbers. It can be the decimals in between, which is what real numbers kind of means, is that it can be those decimals in between. Questions on that? Okay, tomorrow that's where we're going to start, so don't lose it.